In this video, I want to have a look at general solutions to trig equations involving sine. So we're going to derive this general solution in the same, very similar sort of way as we did for equations involving cos. So we're going to start off by looking at the equation sine theta equals a half. So if we've got sine theta equals a half, we could start off by drawing our all stations to central diagram. We know that sine is positive in the first and the second quadrants, and we know that our related angle is going to be pi on 6. Right, so again, we're going to consider each of these rays independently. So if we have a look at this first one here, then our solutions there, if we go in an anti-clockwise direction, so in a positive direction first, our first solution would just be pi on 6. Now if we go around a whole revolution, we'd have 2 pi plus pi on 6. If we go around again, we'd have 4 pi plus pi on 6. And we could keep going, and it would keep continuing that pattern, always with the even numbers of pi. So we'd have 6 pi plus pi on 6, 8 pi plus pi on 6, and so on. Now if we look at that ray again, but if we go in the negative direction, we'd have minus 2 pi plus pi on 6. If we went around again, we'd have minus 4 pi plus pi on 6. Right, so you can start seeing that pattern and noticing that it's always our even numbers that we have, and then we've always got this plus pi on 6 on the end. So if we generalize all of those solutions, we'd have theta equals n pi plus pi on 6, but we also need to write down that n is always going to be an even integer. So it can be 2, 4, 6, 8, or it can be negative 2, 4, 6, 8, and so on, but it can also be 0. So we're going to write when n is 0 or even. Okay, so that's for part of our solution. If we then have a look at this other ray over here, our first solution there would be pi minus pi on 6. If we went round again, we'd end up at 3 pi minus pi on 6. Another revolution would get us to 5 pi minus pi on 6. And you can start seeing the pattern there as well. And this time we've got our odd numbers instead. Now if we went in a clockwise direction for our negative numbers, we'd have minus pi on 6. We'd have minus 3 pi minus pi on 6. So if we generalize this one, we're going to end up with n pi minus pi on 6. And this is when n is odd. So this one's a little bit more complicated than our general solution for cos, because it's a plus when n is 0 or even, and it's a minus when n is odd. So to generalize this, it's going to look a little more complicated. To combine those two solutions, we're going to write n pi plus, and we're going to write minus 1 to the power of n times pi on 6. Now the reason we're going to do that is because if n is 0 or it's even, then this minus 1 to the power of an even number of 0 is just going to be positive. So we're going to have n pi plus pi on 6. Whereas if that power is odd, then it's going to give us a minus 1 here. So we'd have n pi minus pi on 6. So this is combining those two solutions. All right, so to have a look at what that means graphically, I've got our sine curve drawn here, and I'm also going to add in the line y equals a half. So again, our points of intersection are our solutions. So from our general solution, if n was 0 or even, then we're going to add pi on 6. And if it was odd, then we're going to subtract pi on 6. So when it's 0, we're going to add pi on 6, and that's our first answer, is just pi on 6. For pi, that's odd, so we're going to subtract pi on 6. 2 pi is even, so we'd add pi on 6. 3 pi is odd, so we'd subtract pi on 6 to get that answer. 4 pi is even, so we'd add. If we have a look at the negatives, it works as well. So minus pi, that's odd, so we'd subtract pi on 6 to get our answer. Minus 2 pi is even, so we'd add pi on 6 to get our answer there. So you can see how that relates graphically as well. So just to formalize that, in radians, our general solution is n pi plus minus 1 to the power of n alpha, where alpha is our first positive solution. In degrees, we'd write it as 180n. That should be a plus in there, I've just realized. Plus minus 1 to the power of n times alpha degrees. So let's have a look at an example. So our example asks us to find the general solution to sine of theta plus pi on 4 equals minus 1 on root 2. So the first thing we're going to do is just let x equal theta plus pi on 4, which is going to change our equation to sine x equals minus 1 on root 2. Now we can solve this and then substitute back in. So to solve this, we need to figure out what our first positive solution is. So sine is negative is going to be in the third and the fourth quadrants. Using our special triangles, our exact values, our related angle is going to be pi on 4. So that means that our first solution is going to be this one here, which is going to be 5 pi on 4. So that's going to be our alpha in our general solution. So that means we're going to have x equals n pi plus minus 1 to the power of n times 5 pi on 4. Now if we replace our x, we're going to have theta plus pi on 4 equals n pi plus minus 1 to the n times 5 pi on 4. To get the theta on its own, we're going to subtract pi on 4. All right, now we could leave our answer there, and that is correct, but we could also split it up into our even cases and our odd cases, and then simplify those. So if we do that, so we're going to have theta equals, and we'll put our curly bracket in. So we're going to have n pi plus 5 pi on 4 minus pi on 4, and that's for n is 0 or even. Now when n is odd, we're going to have n pi minus 5 pi on 4 minus pi on 4. So that's n is odd. So simplifying that down, we could have n pi plus 5 pi on 4 minus 5 pi on 4 would just give us 4 pi on 4, or just pi. So we'd have pi. Again, that's for n is 0 or even. And if we simplify this one, we'd have n pi minus 5 pi on 4 minus pi on 4 would give us minus 6 pi on 4, which would simplify to minus 3 pi on 2. So that's for n is odd. We could factorize those as well if we want to. So we could have n outside of, not n outside, pi outside of n plus 1. And we could have pi outside of n minus 3 over 2, again with those same conditions. So this is all written as one, and it looks a little bit messier. If we split it into its two cases, then it's looking a little bit nicer and neater. I want to have a look at one more example. This one's going to involve our general solutions for sine and cos. It's also going to involve our double angles. So our equation we're trying to solve is sine 2 theta equals cos theta. So the first thing I'm going to do is replace this one with our expanded double angle. So that's going to give us 2 sine theta cos theta equals cos theta. Now I'm going to move everything to one side of the equation. So I'm going to have 2 sine theta cos theta minus cos theta equals 0. And now I can factorize out my common factor, which is cos theta. So I have cos theta outside of 2 sine theta minus 1 equals 0. Now either this has to equal 0 or this guy has to equal 0. So we're going to have cos theta equals 0 or 2 sine theta minus 1 equals 0. Now to solve this one, we'd use our graph. So we know that cos theta looks like this, and that's 2 pi. Here is pi, we've got pi on 2, and 3 pi on 2. So cos theta equals 0, our first solution there is pi on 2. So because our first solution is that, writing the general solution would be 2n pi plus or minus pi on 2. So that's for this section. We also have to do this one. If we rearrange that, we'd have sine theta equals a half. To solve that one, we draw our all stations to central diagram. Sine is positive in the first and second quadrants. Our related angle would be pi on 6, just like we did at the start of this video. That's our first solution, so that's going to be our alpha, which means that our solution would be theta equals n pi plus minus 1 to the power of n times pi on 6. So the two general solutions for this equation.